Hi everyone, thanks for coming along. So as Anna mentioned, I'm Ryan, I'm one of the tech leads at Just Eat Takeaway, and speak a bit about streaming DynamoDB. So for the next few while, I'd like to cover a little bit about a summary of what DynamoDB streams are, a summary of how we can use them and how we can use them with AWS Lambda and the sort of scaling and infrastructure benefits that we get when we use these two technologies together. And then at the end, we'll take a quick look at some system design practices that you can benefit from pairing these two Amazon technologies together. So first up, a bit of a summary about what Amazon DynamoDB streams are. So the DynamoDB streams are a time-ordered guarantee of every single change event that happens to every record and item on your stream. So when you do any create, update, or delete to any record on your DynamoDB table, the Amazon will guarantee that it will put these change events onto a stream in this time-ordered fashion, and you get the option to see what sort of data appears on the stream. You would either have the data that existed before the change was made on your database, so that's the old image. You'd be able to get the option to have the data that exists after your change is made, that's the new image. Or Amazon also offer you the ability to get both the old and the new image together, and that could be really useful if you ever want to do any processing on this data to maybe understand what's actually changed, and you can process that off the stream if you need to. And finally, the streams have they're totally asynchronous from the actual DynamoDB database table itself, and they can scale independently of each other. So when you ever have any like a large amount of writes happening on your Dynamo table, that doesn't impact the performance of the stream. Likewise, if you have a lot of reads happening on the stream at that moment, it won't impact the ability to have another client or consumer read or write to the Dynamo table itself. And like all of Amazon's serverless technologies, by default, the stream and DynamoDB database itself is split across multiple availability zones, giving you that really high availability that Amazon can offer you in any given region. So what does a DynamoDB stream look like? Once you've made a change to your database, the records, the change records of the items get added to the Dynamo stream, and the stream is broken down into a few parts. You've got the actual main stream itself, and then inside the stream, you've got something that we call a shard, and that is essentially how the stream scales up itself. It will add your data to different shards across the stream so it can continue to spread the load evenly. And then you've got the individual records or pieces of data on the stream. And each one of these data blocks here is an individual change to an individual record on a Dynamo table. So every single create, update, delete item will result in an individual item being added to the stream. So when you're actually going on to consume the stream, you consume the individual shards itself. So when you query the Dynamo stream itself, the stream returns a collection of shards. And this collection of shards gives you like an iterator ID, and you then have to query that individual Dynamo shard ID, and then you can start to get the individual pieces of data off of that shard. And a shard is really just a representation of the partition data that you've got on your Dynamo table as well. And like with a lot of different streaming technologies, so something like Kafka or Kinesis, you're able to start consuming data off of the stream at various points. And DynamoDB streams are no different. So here we get the option for trim horizon, which is the very earliest record on the stream. It's important to note that Dynamo streams maintain their data for about 24 hours, and then after that, they start to fall off the stream. So when you do start at the trim horizon, it's the earliest record that you've got, that will be up to 24 hours of data that you could then start to process. We've got the latest, so that is when you start processing the stream, that'll be the very start of the latest record that's been added to it there. And then we've got at sequence number, which is I want to start processing at a specific given point on the stream, and after sequence number, which is exactly after that specific given point on the stream. So with every serverless technology that is provided by Amazon or AWS, you're often only ever billed for exactly what you use, and Dynamo streams are no different here. So when you're actually querying the stream, you actually only pay for essentially the API calls to get the data from it, setting the stream up and having the data on it's free, and you only pay for the consumption of this data. So you can call this get records API, and that will return up to 1 megabyte of data from the stream. And for this, you get 2.5 million free read requests a month. And then after that, it's an extra 20 US cents per million. I think that might vary a little bit between regions, but it's usually around this point. However, when you're actually consuming Dynamo Streams with Amazon Lambda, there is actually no charge at all for making these requests. The total cost of using a Dynamo Stream when you're consuming it with Lambda is all built into the pricing models that Lambda and the DynamoDB writes itself already charge you for. So when you are actually consuming data with Lambda, there is no additional cost for using a stream. So you can start to think about some of the really powerful patterns that you can build out here without actually having to incur any additional costs. So just before I move on to how we actually would consume this with Lambda, I just want to pause for a second and see if anyone's got any immediate questions about DynamoDB streams. If not, I'll just move straight on to Lambda. I guess doesn't look like it. So we'll be plenty of time for questions at the end as well. So next, I have a little bit of a talk about how you can actually go on to consume this data with Lambda itself. So like with lots of Lambda integrations, you get the asynchronous or synchronous types, and this is one of these asynchronous event sources. So sitting in between your actual Lambda functions itself. So Lambda, I guess, is the serverless function as a service offering from AWS. So in between your Lambda function and the actual Dynamo stream, we've got something called the event source, and this is what is essentially polling your stream. And I mentioned previously that the stream gives you 4 different places to start consuming data from. When you're using it with Lambda, you only actually get the option of 2 here. So you can either start at the earliest point in time, trim horizon up to 24 hours in the past, or latest, which is exactly right now and everything that happens after this point in time. And then when you're scaling your stream, the stream and the Lambda functions can scale independently of each other if they need to, because it's a nice and decoupled system. But as the number of partitions on your Dynamo table starts to grow, you will get more shards added to your Dynamo stream, and then you might need to start to increase the number of Lambda functions that you have processing this data, just to prevent any sort of back pressure you might get in your iterator on this stream never actually managing to process it as quick as records are getting added. So it's something to keep in mind there, that if you do ever need to use this, Amazon offer a CloudWatch metric that you can monitor for the age of the oldest iterator. And if that ever goes over maybe 15 minutes or 1 hour or something, you could get a notification to let you know that you're not managing to process the stream fast enough, and you should maybe think about scaling up your Lambda functions. And of course, when you're using Lambda, everything's fully managed for you. So with this event source, you never actually need to take care of any logic to understand or remember how far through processing this stream you are. Amazon guarantees the items go onto the stream. Amazon will also guarantee that this event source will attempt to process it and will hand it off to your Lambda. So it just allows you to really focus on only having to code your business logic and the actual implementations that you need for this data. And you don't have to worry about infrastructure. You don't have to worry about making sure that you're maintaining your position along the stream or anything like that. So a quick look here at what might actually happen. So over on the left, we've got our DynamoDB table, our database, and then we've got any sort of insert, update, or delete happening on the table, and all of our Amazon records are split across various partitions on the table. So when a record on the A partition, for example, is changed, it will always be fed into this shard here, shard number 1. I guess these are all just arbitrary values. And then the Amazon event source that's calling this get records API will make sure that shard 1 is always passed off to a Lambda function, and you would never get this Lambda function processing data from different shards at the same time. And that's just to allow and to help make sure that this time order guarantee gets maintained when you're processing data. So you would never process data from record 1, 2, 3 and update after a delete if they happen in different orders. And Lambda gives us different ways that we can actually consume data off of the stream. So we're able to batch some records. So this event source, this poller, is able to sit there and essentially wait until there are up to 10,000 records of change on the stream before it hands that off to your Lambda function for processing. And you can combine this with a batch window. And a batch window is essentially us telling the Lambda service to wait for up to 5 minutes or 300 seconds before it takes any data. So you might have a situation where you want either up to 10,000 records or wait 5 minutes, whichever one happens first. You then get sent your payload to start processing with your logic. And you also have the ability to increase the number of batches per shard as well. So on my previous slide, I had one Lambda function attached to one shard. You do have the option to increase these as well. And behind the scenes, Lambda again does some things to make sure that you always get records in the same order. So you always get a nice time series order of your changes on your table. Unfortunately, as with anything, mistakes and errors can often happen. It could either be a bug in our code, or it could be maybe a downstream dependencies unavailable at that moment. So we should always keep in mind some of these error handling strategies that we can use. So we get the option to set what we call a max age and retry. So that is the maximum age of any given record that Lambda would attempt to process. So if you maybe say set this to 1 hour, once a record's been on the stream for more than an hour, even if you haven't got to it yet, the Lambda service will just skip over it and move on to the next record that's within the time, the max age time bounds that you've got set. And we've also got max retries as well. So for any given record, you can say that you might only want to attempt to process it 5 times. And if you can't process it after 5 times, then it just will move past there. An interesting and useful error handling strategy for these batches is you can split on error. So as an example, if we were using a batch size of 100 and there was an error anywhere inside that batch, we would return an error from our function or throw an exception. And then the Lambda service would essentially split that 100 item batch in half and then only give us 50 to retry. And if that errored again, it would split it in half again and then only give us 25 to retry. And you can start to combine this with some of your own logic to understand that try and narrow down the error to eventually you could narrow it down to a single record that's broken, and you could maybe handle that single record in a special way and then continue to try and process the other 99 again until you can successfully process them all and then continue on down the stream processing the data. And finally, there's the concept of failure destinations. So that is when your items hit either its max age threshold or its maximum number of retries. Amazon Lambda offer us the ability to essentially send the failed error metadata records to an Amazon resource. So that could be SNS or SQS. So it's important to note here that they won't actually send the whole record. They'll only send you metadata about that record on the stream. And we'll have a look at that in a sec. But this allows you to monitor and alert and be told about any errors that are happening and capture some of the data attached to these errors if you ever need to inspect it either visually or have some other computer system inspect it again in the future. So the metadata that Amazon would actually put onto one of these error failure destinations it's this failure metadata here, and it contains a couple of useful things that you can use to try and correlate some of these errors across your system if you need to, or to try and understand what might have gone wrong with it. So we can see, first of all, that they tell you the condition, so the reason that Amazon has failed this record, and we can see a retry attempts exhausted, and we've got an approximate invoke count here. So it seems like in this scenario here, we may only ever want to have one retry on this item. Once it's been attempted to be retried once and it still failed, then it would hit this condition and we would send it off to this failure destination, and we could inspect that later if we need to. Then we've got a start sequence number and an end sequence number. So this could be used if you needed to try and then go back to the stream and inspect it, specifically if you ever needed to. So back at the start, I mentioned that you can consume a stream or a shard at a given sequence number, and you could use this sequence number to then go and grab that specific record off of this stream if you ever needed to. Or you might want to use this in logs to see if maybe what the record right before the sequence number was, and then the record right after the sequence number was, if you are logging these sequence numbers in some way that you can read. And we've got the stream ARNs. It's just some extra information that allows you to really quickly see, it was this particular stream or this particular table that has failed, and you can do anything with that if you need to. And finally, this one is a really interesting and new way to manage some of these failure scenarios that Amazon announced in 2020 at reInvent, so about 6 months ago. And it's the ability to offer this so-called checkpointing function. So this is the scenario where maybe if you did take a batch of 100, you might have the ability to process maybe 99 of those records. And then if you get the 100th one failing, you can return from your Lambda function the fact that 99 have actually succeeded, and it's only this one record that's failed. So the stream processor will still be able to move past them on the stream and will only attempt to retry that one record again. So I think it's something that could really make the error handling and retry functionality of streams and Lambda really useful. And yeah, this is just here. We would return a sequence number from our Lambda function to say this is how far down the stream we've got. Don't send us these records again. We have successfully processed them. So that was a quick summary of how we can actually consume Dynamo Streams with Lambda. And then I'll quickly cover some design patterns that where these two features or Amazon capabilities work really well together. But I just want to make sure that I guess everyone can still hear me okay just before I jump into the next section. I guess no one's mentioned there's any problems, so I might just carry on.
Yeah,
cool. So yeah, I'll cover two different design patterns or strategies that we can use that really utilize some of the features and functionality and scalability that Dynamo and Lambda offer us. So first, let's have a quick look at what maybe a microservice is and how we might use it. So one of the key concepts of using a microservice is to allow decoupling between systems, that in one scenario, if one system breaks or goes down, it doesn't take with it other features or services. So in this example that I'll use here, I've got to imagine that we are working for a food delivery company. And as part of this, we might want to offer our restaurant partners the ability to say that they've maybe run out of cheeseburgers, or they've run out of stock of cheeseburgers on a Friday night, and they want us to basically stop allowing customers to add cheeseburgers to a basket. So we might have this out of stock service here. This might have some sort of API that allows restaurants to say that they've run out of cheeseburgers. We would store that in our local database, and then this would be one microservice. And then we would use event-based systems to decouple these two services from each other. And then we would have maybe a basket service somewhere else that might want to understand whether or not an item is in stock or out of stock. So using microservices, decoupled event systems here allows us to make sure that if this service ever goes down, the basket service is still able to operate successfully. So one of the ways that you can build an event system or a type of event that you might have is a so-called event carried state transfer type of event. And this is essentially a really fat event that you would publish that contains full details about any given entity with what it looks like after anything has changed. So if something ever changed on your system, you would publish this event using this event carried state transfer strategy. And that would allow all these consumers to know the full details about the event, and they wouldn't have to call back to the publishing service to understand this. So in this example here, the basket service might get an event saying item ID 123 is cheeseburgers and it's gone out of stock. And the basket service never has to actually call back to this service to understand that event. It gets the full details all in the payload. So this might increase like data and storage use across an entire system, because you now have several systems all essentially having copies of the same set of data, but it does massively improve reliability and just further enforces this decoupled nature of your platform. And storage is getting really cheap these days, and it's often better to pay for a little bit of extra storage than it would be to have your entire platform going down because one system wasn't able to stay up or one system went down. And so where does Dynamo come in here? As I mentioned at the start, Dynamodb Streams have the option to allow this new image to be projected onto the stream. So that's essentially us saying to Dynamo, when someone updates a record in Dynamo, you might only update an in-stock or out-of-stock Boolean flag, yes or no, but you could publish that whole record. So you would get the ID, you might get the name, you might get the Boolean true, false, out-of-stock value. All of that you could put onto your stream, and from your stream you can maybe have a worker processing it and publishing it out again. So you wouldn't even need to have anything doing any reads of your Dynamo stream, and then anything consuming further across your system wouldn't have to call back to your Dynamo table either. So you can keep the reads on your Dynamo scaled down as well if you need to. One of these cost saving measures as well that just benefits from using serverless systems like this. So just down at the bottom again, I've mentioned you could have your systems consuming the Dynamo stream directly, but that's something that Amazon don't recommend. There are concurrency limits. You can only have 2 stream processors at a time. So it might be better to then integrate a Lambda function that consumes your stream and then publishes your data out. So a really nice pairing between Dynamo and Lambda here. And then the second, I guess, microservice system or strategy that you might have to plan for is this so-called producer-consumer correctness problem. So this is a situation where you might have one service maybe doing too many things and some of your system might become out of sync. So in this example, we would have our restaurants telling us that they've run out of stock of an item. We would write that to our local database. So this service is now fully up to date. But then we try and publish a message to SNS. But for whatever reason, the SNS service from Amazon is down and we fail to publish the message. We would return an exception to the client, but we have really no way of guaranteeing or enforcing that the client then goes on to retry. We would hope that they would, but you never know, they might not. So at this point, the basket service might think that cheeseburgers are in stock and our out of stock service thinks they're out of stock. So when the client maybe goes on to refresh their data, they would see correctly that, great, they think they've marked it as unavailable for that night, but they're still getting orders with cheeseburgers in it and they get really annoyed. And that's because we essentially have an out of sync system at this point. And that can become a really big problem when you have wide spanning or large event-driven decoupled microservices. So how could we fix this from happening? So again, Dynamo and Lambda is a really, really great way to stop this from happening. Using these two together, we can be ensured that all consumers of a given service are always kept up to date of a change, and we decouple the concept of writing to our local database and then publishing our event out across the platform. So to get around this problem, this is how you can maybe design a system like this. We've still got our HTTP requests getting written to our API and writing to our database. And at that point, we can just return a successful status to our client. We have updated our database. And at that point, we can almost guarantee to them, we will update the rest of the platform at this point. So we've added it to DynamoDB, and DynamoDB and Amazon guarantee that that will go onto the stream. And you can guarantee that the stream record will get sent to your Lambda function. So we can then have our Lambda function handle that message and then publish our event carried state transfer event of the full record to across the system. And in this case, the basket service would handle that message and update its local cache or its local projection of that data. So by building services out like this, it allows us at every point along here, we can independently scale the API here. We can independently scale the database here. We can independently scale this Lambda function if we need to. And the basket service can also independently scale its handling of these events if it needs to. So it allows us, to really start building out really focused, specific single responsibility functions and systems that utilize some of the service technologies that Amazon give us to build a really nice decoupled, massively scalable solution to allow any sorts of services to interact with each other. And this is actually a small example of some of the services and design patterns that we are using at the moment at Just Eat Takeaway. So it's really interesting for us to see how well that these can scale, especially as our traffic patterns vary really wildly during the week, Saturday nights and things like that, really, really busy. So that's everything that I wanted to talk about. A quick look at what a DynamoDB stream is, a quick look about how you can use these with Lambda, and then at the end there, a couple of slides just on some of the design patterns and architecture styles that you can use to utilize these functions to really scale out. And yeah, I'd like to point out as well that Just Eat Takeaway are currently hiring. If you are interested in working with AWS technologies at really, really large scales, high throughput systems, event-driven systems, please get in touch with Katharina at Ciklum. You can scan this QR code as well. I think that'll take you to a careers page or a page about some information. And if you've got any questions about Just Eat Takeaway or things I've spoken about there, I'm super open to answer any questions now. Feel free to follow me on Twitter and we can pick some stuff up off asynchronously offline if we need to. Thank you very much.
Okay, if everyone don't mind, I want to start with questions. Right for now, we don't see any question from chat. Guy, please, if you have a question, please send it, because I have a lot, so I can spend for an hour time slot for questions. Ryan, first question is some general information. Basically, for you, it's not just a theoretical knowledge, but practical. Based on your experience, real experience, what's the issue, main issue, what you're faced with working with DynamoDB streams?
Yeah, so we haven't had any major issues yet. We've been running a system really similar to this in production for maybe 4 or 5 months now, and it hasn't errored yet. But one of the things that we did consider when we were building these was what happens in the world where maybe SNS goes down. So this Lambda processor, it's really, really thin. It doesn't do very much. It just forwards the message straight onto SNS. But if SNS ever did go down, what would we do in this situation? So we've got a couple of strategies in place that we are using right now to try and stop this ever happening. So I guess that's the problem with things coming out the other end. We haven't experienced any issues with things going in at the moment either, but one of the things that we're always conscious of is this back pressure concept, that more and more data is getting added to the database quicker than we can process the stream. And when these things start to back up and we can't process them quick enough, then we need to scale something, this Lambda processor, out to make sure we can deal with it. We do have alerting and things like that in place. So if a problem like that did ever come up, we would be alerted to it as engineers, and we can go and scale something that's necessary if we need to. And as always, we work with some of our product teams to make sure that our service level that we're providing is at the appropriate level. So maybe restaurants expect things to be out of stock within 5 minutes. So we have 5-minute alarms set for record length and things like that on the stream. But so far, it's working really well for us. And we're rolling out this concept of Dynamo Streams, this whole pattern actually, in a few other teams at the moment.
Mm-hmm. Okay, cool. And again, I just can't ask this question. If we speak about streams, it's always come a question about Kafka. What do you think? So if I am from an architecture point of view, if I should decide what to use, DynamoDB streams and Kafka streams, what's the benefit of DynamoDB?
So at reInvent again last year, so it's 6 months ago, Amazon offered the ability to essentially stream data out of your Dynamo database into a Kinesis stream. So I guess Kinesis is Amazon's like serverless Kafka equivalent, or the closest thing they've got to something like Kafka. And I think with all of these things, it's just always the right tool for the right job. Part of the reason that we use Dynamo Streams here is that it's more mature than Kinesis and Dynamo's integration at the moment. And I know that Kafka is a really well-established product, but we didn't necessarily want to have an API having to write to a database and then also write that onto the stream as well. So we just looked to see how we could make the API be as quick as possible. The only thing we needed to do is write to the database, and Amazon take care of then adding that to a stream for us. So it just allowed us to decouple some of the things that we need and not introduce any more moving parts to our infrastructure. On the actual Kafka subject, Kafka isn't super widely used at the moment inside Just Eat, which did impact our decision a little bit there, but it is something that we're always evaluating and looking to use. And I know there are some teams already experimenting and trying to understand Kafka. But yeah, I think it's just one of these right tool for the right job. And we were able to get everything we needed at a super low cost that's really scalable by using DynamoDB and the streams out of there.
Okay, cool. And by the way, I see you mentioned that AWS have a Kafka service for Kafka in AWS.
Do managed Kafka service. I think, yeah, literally just called managed Kafka service. I think with a lot of things, yeah, really good. Again, it's not one of these serverless technologies, and a lot of the teams that are using this prefer to be in the serverless space just to get around any problems with having to manage infrastructure and things. I think you still have to provision instances to run your managed Kafka stream service. That's a mouthful.
Yeah. Okay. Yeah, I think it's really related. Like we have for Kubernetes, EKS, and for Gate, something like that. And again, if we so. What also Kafka mentioned always, it's about at least one, preventing duplication. What can you say about DynamoDB? So do you have any problems with at least one delivery about duplication protection?
About what, sorry, duplication protection?
Yeah. So if you, for example, we say we need only one message and not to duplicate this message.
Yep, so there's, I think, two sides to that question. I guess first, the rights to Dynamo. Would we ever write things twice? Would things ever get on the stream twice? But also the downstream services getting duplicate deliveries of these changes. So when we're writing to Dynamo as a practice internally, some of the really nice things about Dynamo is that you can do conditional updates. So we capture timestamps in a lot of places. And when we update a record, we make sure that we're not updating a record with potentially older data than it already exists in our Dynamo table. So at that point, we try and make sure that we're never getting stale data written to our database itself. Then when it comes to things going onto the Dynamo stream, a guarantee from Amazon is that things will, one database write will always result in one event on the stream. And you will never get double or duplicate deliveries on the stream itself, which makes it really easy for our Lambda processor because you don't have to necessarily think about this item potency problems at that point. And then when we go on to publish these SNS events as well, we publish all of our messages with a timestamp, again, to make sure that all of our consumers of these changes never process data that is potentially older, stale, and to also make sure, it helps them make sure that they never have to process duplicate events. So that's one of the things you always need to keep in mind when you're using SNS is that Amazon guarantee at least once delivery, but you may quite often get more than once one item delivered. If you do need to guarantee exactly once delivery out the other end, you could use maybe a first in, first out Amazon SQSQ, which offers some more of those exactly once delivery protections.
Cool, thank you. So Anna, I think we can go forward because I don't see any question. And after that, we can on panel discussion continue our question, at least from my side.
Okay, thank you, Ryan. Thank you, Alex. And now I would like to pass the floor to Vitalii. So you can share your presentation and
thank you, Anna.
Start.
Just a second. Let me know if you can see.
Yes, everything is good.
So yeah, thank you, Anne. Thank you, Ryan. So let's maybe start with another topic, and that is a more oriented on the data services. So I'd like to share with you my experience of building the data services in AWS Cloud. So at the moment, here my position is the head of Data and Analytics Center of Excellence. I have good experience in solution architecture, especially for data lakes, data services, fast data systems, BI systems. So in total, my experience is more than 20 years. And last 5 years, I was a solution architect for huge companies. And my previous position in my previous company was head of enterprise cloud solutions. My team was responsible for migrating from on-prem to cloud mostly for the data platforms, data science platforms. If you're talking about the agenda, so the presentation I prepared for you today, it's mostly oriented on the real cases we had. And that is three cases, by the way. The first one is about low data latency service in AWS Cloud, how we actually did it. And I'll just share the architecture, the approach, and the way how we optimized the service. The second case would be about the data science platform for customer single view. And the third one would be the huge data lake with the data computation and machine learning layer for the investment company, for the huge vendor. So I would finish this presentation with a way how we train people in Center of Excellence, skill metrics, and what exactly you need to know just to be a good data engineer if you'd like to actually. So first of all, let me start with the services currently present in AWS platform. So if you're talking about the data platform in general, there are three segments. The first one is a major segments of services. The first one is data visualization. And here we have tools mostly for data, I would say, showing the dashboards, building the dashboards, and presenting the reports. So sharing the reports between different end users and the roles of end users. The second segment is the machine learning. And here we usually have two types of components. The first one is responsible for training models, for extracting features from historical data and preparing the models as the final result of this service. And the second one actually is model scoring, when we have the usually models published as microservices with REST API. Data is coming to these services, and the outcome is a result of predictions, kind of segmentations, or clusterization of data that is coming from actually clickstream or some other kind of real-time data ingestions. And here on this slide, you see the storages. So this third segment, storage and the data processing. So in AWS, the storages are mostly built around the one service, which is called Amazon S3. And there are several components that actually operate around this service. And there is a AWS Glue, which is kind of ETL tool. With AWS Glue, you can connect data source and data destination and create the data transformation pipeline. Another one is a combination of Amazon Kinesis and AWS Lambda, which is a way how you can build the real-time data processing. And the storage, Redshift, it's a way how you can build the data warehouse inside the AWS cloud. So there is a way of building data lake when you don't need to put everything to the Redshift, and some data is still present on S3. To query this data and have the SQL interface to the files on S3, the best way is to do that actually to use Amazon Athena. And the Spectrum, Redshift Spectrum, is a component which actually gives you possibility not only to access Redshift, but with the same query, like you combine together the data present on S3. And the last service I would like to talk about is EMR. EMR is a service, actually the cluster coming from the old Hadoop world, when we had actually the combination of computation and the storage layer on the same cluster, and used actually Spark for preparing data for analytics. And in this actually EMR service, we have the same approach, but the computation as a computation layer is used Spark, but the storage layer is presented by Amazon S3. Every time we work with architecture and building the infrastructure inside the AWS cloud, we refer every time to the information schema, information systems, and business architecture, because it's very important to understand why you're building these systems and how the outcome from the data preparation and data calculation will be used by end users. So that is why every time when we have the kind of workshops and discovery with our clients, we start with the business layer and understand if this business layer actually prepared and organized in the right way. So in the business layer, usually there are several components like processes, organizational structure with offices and their services, and understanding how the process actually connected together and transfer data between services. Then we go to the information system and understand which actually component, which services are covered by different products. And when we understand the product and we understand the systems inside the organization and understand how the processes are implemented, so then we go to the technological architecture and propose changes inside the technological layer. So to do that, actually, we use the TAGAF framework, and you see the general approach of the TAGAF when the requirement management is divided on the different components, and each component actually provides the requirement management for specific layer. So going to the technological layer, we usually have the set of requirements from business. We have the goals, targets, non-functional requirements, where we understand the quality attributes and understand the budget for the future system. And today I'd like to talk about three cases. And in each case, actually, we used this approach. We try to understand what exactly actually our clients would like, wanted to build in the AWS cloud, and how the results of those systems, actual outcome of those systems, help them in business. So the first case I'd like to talk about is a low latency service. So to be honest, the system was present, and our role here was to improve this service in terms of performance. And if you're talking about the business case, so the client actually built the website. It was a traveling company, the website where the reservation for the hotels are presented as a service. So the end users could send a filter and define the list of hotels that can be reserved by the user. And as you see, the service was actually combined with the two services on AWS site. So the first one is a product catalog, and the second one is a P&A, which is a product price and availability. So every time you see the item on the website, near this item, you also see the specific information about price and the availability of this service. I mean, just availability of this item, like in product stock information. And in case of hotel reservation, it's a very specific information just because it depends on duration and the specific date when you're gonna start being in this hotel, and there's a start date, I mean, and how long you're gonna stay in this hotel. And also it's very important to know the type of room and total count of actually guests that are going to be in this specific room. So that is why that is a quite complicated combination of two services. And every time you check the availability and price for the hotel reservation, you need to also send the filter from the website. And if you see the requirements for those two services, so you understand that the amount of data is not really huge, only 250 million rows in a database, and 400 requests per second for the P&A service. But in general, what we saw actually, the response time was really huge. I mean, slow. The service was slow, more than 10 seconds for each request. And that was quite surprising for us, just because the target response time was defined like 1 second for this service. And the company in general was in a moment of transformation. They started decoupling all the huge legacy application to Java Spring, microservices, Dockers. So they use Kinesis, and they use CQRS model. And our role was to understand where the bottleneck is and propose the way of optimization and present the recommendation of the architecture in general. So maybe a few words about the CQRS model. So if you're not familiar with this, each service in CQRS is presented like two interfaces for command and query. It's very important to understand those two data flows, just because usually inside the service, inside each service, there are two databases. The first one is called command, the second one is called query. And command, it means the interface for any changes in data when you need to update some information or insert new. So actually the command interface is used for that. But every time you need to get information from the service, there is another interface for that, which is called query. And that's very specific approach, just because it gives you not only way of scaling databases and using even different databases for each flow, for command and query, but also to create a way of communication between services, which is called event sourcing. So it means that inside the infrastructure, you can create the kind of event bus that could be built on top of Kafka, Kinesis, on any other RabbitMQ and any other queue actually system, and send every time you have some kind of event, like a command, create an event and send this event to this queue. And subscriber will take this event, which could be another system, and update the read database, query database inside the service. So actually, this approach was implemented on a client side, but the client actually wanted to use Aurora DB for both services. So our task was to understand if this is the right approach or we need to change something in the technological approach as well. So if you compare two databases, Aurora DB and Dynamodb, so they're in terms of scalability almost the same. They are very fast and provide the low latency data access to the rows inside the database, but in general, the interface of those databases are absolutely different. So Aurora DB is still RDBMS, Relational Database Management System. It means that the data inside the database is presented in a way of tables and relations between them. And if you need to take data from the database, you need to create a query in SQL and send this query to the query engine, to the database. And in case of Dynamodb, it's absolutely different approach. It's a key value storage where you look up data using some specific partition key or just key and get it like mostly in a lookup way. So if you follow the best practices from AWS, it's better to use Dynamodb for command database and Aurora DB for query database. And in this specific case for this client, that was the best approach just because the query was quite complex and the queries actually changed really fast, and the filtering and sorting inside the database was used between different queries and different requests. And the way how we can improve this model, how we can make the journeys between them really fast, it's a flattened table. So we made as most flattened tables as possible. Also, we made changes in a way of architecture. So after the series of POC, we understood that the main problem is the size of request for each request. So in a worst scenario, the size of request could contain 4,000 accommodation ID inside each request, which actually made the queries really huge, and even parsing of those queries and creating the execution plan took longer than 1 second, which was absolutely unacceptable according to the requirements we had. So we decided to split those queries by 50 IDs, and also we implemented the way how the request itself was divided by smaller requests and sent to different shards. So also there were some changes on flattened table. So we added more pre-calculated columns. We created indexes on those columns because in a relational database world, it's a good approach to create indexes on columns. And also we improved queries. So we changed the way how we sorting data, how we filtering data, and inside the queries, inside the text of queries. The last POC we had showed the good results. So 40, 60, 70, milliseconds as response time for the for 800 accommodation ID inside the request. So that's the case of architecture improvement. So everything was implemented inside the AWS, and we used Aurora DB and the securest model for the architecture. Another case I'd like to talk about is a customer single view. So the clients actually wanted to create the system where the whole information about client is consolidated in one place and shared on one dashboard for each client. And that actually was an interesting request, just because the information was spread by different systems, like a CRM system, web databases for web services and the mobile services, and also the huge amount of data was stored in transactional database where there was orders and clickstream. So the whole information, the all data should be actually consolidated to one place, to one data lake, and also the custom dashboard needed to be built on top of this data lake and presented the visualization of data, and also presented the computation layer for training models and making some analytics for marketing, like segmentation and the prediction of the shopping behavior. So after the actually consideration what would be the best platform for that single customer single view, we decided the Snowflake with a combination of dbt and Airflow would be the best one, just because everything was defined like a schema. I mean, just we didn't have any surprise in structured information. Everything was defined by a schema, and it would be easier for us to create tables and create the scalable enterprise data warehouse. Also, Snowflake is the best approach probably for building enterprise data warehouse in AWS, just because it gives also possibility for real-time integration with the S3, like an event collector. And also dbt is another way how we can build these models and ingest data and process data inside Snowflake in real time. So in general, we started this project, and we also created the academy for that. And it's really difficult to find at the moment specialists who are familiar with Snowflake and have good experience with this technology, just because it's very trendy, and everybody would like to have those specialists in their organization. So we started this academy, and we train people in Snowflake, and the requirements for that is only be familiar with AWS data platform. And the last case I'd like to talk about is data science platform in AWS. So it's a venture capital company, actually as a client, and they wanted to monitor millions of potential investment in the internet, and they decide whether investment would be more efficient. So our role was to create a data lake with actually with a series of pipelines inside the data lake to form the investment portfolio, and also to create and train machine learning models to understand whether investment will be more efficient. And those recommendations for machine learning actually integrated with the Salesforce, where the end users can see the actually the consolidated data about investment portfolio and the recommendation from machine learning system. So we've been working on this project for more than 3 years, and they created the quite complex, I would say, system inside AWS. So there's a data lake with different layers. So the raw data layer, the data warehouse with normalized data, and the data warehouse with a certain layer, I would say, where data is ready to integration with other systems. So the internal engine for that is Lambda functions, and also we use EMR just to train models and extract features from the raw data. In general, the final result is actually saved to the Postgre database and integrated with the Salesforce system on the on-prem on the client side. Few words about the learning paths and the career paths inside Ciklum. So in this Center of Excellence, we have a skill matrix and all processes for growing our specialists, not only hiring them. And from junior to expert level, we have a career path, and every half a year we have a performance review with our specialists and define the gaps between the levels and how they can be grown from, for example, junior to senior. And as you see, there are two streams after senior, which is a managerial stream and actually technical stream. The same career path in details. Inside the Center of Excellence, there are actually three streams: data management, data science, and IoT. And for each, we have the transition between layers and between levels and between positions, between streams. So talking about AWS Cloud Engineer is a part of data management. So there are required skills and skills we train. So for required skills, we define AWS Data Platform, SQL in general as a language and approach in a data warehouse, data modeling. Other skills we train here at Ciklum using Academy approach, and among them BI, Snowflake, dbt, Lambda, Data Vault, Docker, Elasticsearch, Git, Kubernetes, and Python. So if we look at the way how we train people, so we propose to actually to be part of to join the academy, data academy, where we have different streams, and 3 specialists at the moment operate and are involved in this process: the head of unit, head of data management unit, the learning development consultant specialist who actually coordinate the whole academy, and also the technical specialist who are responsible for answering questions and mentor for the participants. And during 4 weeks, we have the intensive training. We use Udemy platform for that, for tracking and for presenting actually courses. And after that, all participants are certified and they're ready to join the projects. Even during the project period, during the working on the project, when they have the onboarding, so they still can continue studying some specific courses, and usually they study Python just because it's too difficult to learn Python in 4 weeks. So that's it from my side. If you have any questions. Ready to answer.
And again, thanks from my side also for you, because again, practical cases is always cool. And before I don't see any questions, I start from my side. Okay, so as soon as I hear about AWS Lambda, and after that you mentioned that this project was on the Java stack. Question from my side is about cold start. So how you work with AWS Lambda and how you fight with cold start for Java application, Java Lambdas?
Yeah, talking about the first case or the last one?
No, just in general. So we don't have, let's say it's a general fact that, for example, if you use Lambdas, mostly if you don't want to have problem with performance, use Python, because without any cold start, it's interpreter language, yeah, let's say. But if you are using Java, maybe I missed something from your slide. On some slide, it's mentioned about a technical stack, Java, Spring, and also about Lambda. So I make an assumption that you for Lambda use Java stack.
Yeah, well, for the first case, for Lambda actually was used Java Spring, but for the last one where we designed everything from the scratch, we use Scala, and that's our common approach here. So it's really difficult at the moment to find specialists good at Scala, but we still go with this language, and all our pipelines at the moment are built on Scala. It's because Scala is also good for Spark. I mean, just like one of the languages in Spark, it's Scala, and the next one is Python, PySpark. So that is why Python and Scala, I would say, the languages for data engineers.
Okay, cool. Next question about CQRS pattern. It's also interesting situation, because also on slide when you describe CQRS approach, it's also someone mentioned about previous approach, let's say from age begin, it's just split on read-write database replic, etc. So my question for you is about what for you key metrics when you start thinking about, okay, apply or not apply CQRS approach for your application?
Yeah, the good question, by the way. So first of all, we need to understand how we're going to communicate between services. Are we going to use the event bus, or that would be like in a CQRS inside the one application? I mean, just inside one service. In this case, when we have event service and everything is transferred to the like an event to the event bus, so it's one way how we can communicate between services. But in this specific case, in this specific I would say for this client, they still had the communication on the REST API. So it means that every time we have some changes in the microservices, the event is published to the event bus, and then using the REST API is implemented to the command database. So that's probably not the best way how we can implement it, but in general, the CQRS and event services is the right approach of communication. Talking about the databases, it's very important to understand how the consistency between those databases would it be eventual or not. Just because if the data actually present in the query database should be absolutely consistent with all changes and events inside the system, probably the CQRS approach is not the best one for that. For example, in this case, the reservation that is coming as a command to the P&A service was not so important. I mean, just shouldn't be consistent with the database, query database. That is why the CQRS approach was good for that specific service. But in general, if you're talking about the stock information, so probably eventual consistency is not the right way. If you're talking about, for example, near real-time availability of the stock data.
Okay, thank you. And we have a question from Ryan, and Ryan asked a question about the CloudFormation Terraform. So what's the management tools you are using, mostly using for infrastructure management, and what's the pros cons you see for each of them?
So generally, we follow the approach from AWS, and that is actually CloudFormation. So if you're talking about so at the beginning, I would like to say that the best probably approach to use Ansible still, because it's a right way of building the data pipeline and building the deployment pipeline to the cloud. So in my previous company, actually, we used Ansible for the real long period of time, and we still support this approach, even if we're having some kind of data science and data model training platforms in EKS. At the moment, Terraform probably would be the best way, and as I know, all systems at the moment are transferring to Terraform, and we follow this approach, and Terraform is a part of any deployment pipelines at the moment.
Okay, yeah, and by the way, Ryan, if you have some additional clarification questions, please. But if I understand correct, it's based on situation, but in general, Terraform right now, it's a best item to choose. Yeah.
Right.
Okay, cool. Next question about academy courses. So it's for everyone, developers who already assigned it, not assigned it, or it's just for some, you know, for some intern who decide, okay, I should go for this project, and after that, only for this candidate, you provide these courses, or it's availability for everyone? Yeah,
thank you. So yeah, that's for everyone, and even if you're not a data engineer and you'd like to be a data engineer, so you can enroll definitely. The only thing that we check in before assigning this to this academy is a required skill set, which is the AWS data platform, SQL, and the data warehouse data model. It's just because it's impossible to train those skills in 4 weeks, even in 2 months or even 2 years, and that should be kind of experience. And if you're talking about the junior developers and middle developers, probably we can train those skills. But if you're talking about the senior level, so those skills should be like a huge fundamental foundation of the specialists. And we assume that people actually had good experience more than 3-4 years in those technologies, I mean AWS and SQL. So I mean, if you are good at SQL, if you had experience in data warehouse building and modeling, and if you are familiar with AWS data platform, with such components like Dynamodb, Aurora, Kinesis, so probably it's you are the best candidate for this academy. Even if you don't have experience in this, we have courses for SQL, for data warehouse and AWS data platform. But again, it's important to understand that the level of the specialist would be on a junior, middle, not senior.
And also, how can I see that it's mentioned about Python? So if I understand correct, and also my previous experience that for data engineering, Python, it's a priority language. But also on this meeting, you mentioned that you are using Scala with this Spark. So it's a limitation that a person only with Python mindset, skill set should come.
So at the moment we're trying not to use Scala and Java for the data transformation, but only Python and SQL. It's because the modern data world is going to Python and SQL. So previously we had, I would say, situation when almost all data transformation pipelines, especially in Hadoop, were built in Java and Scala, but it was quite complicated just because data scientists, actually for data scientists, it's very difficult to study those languages, and quite strange situation.
Sorry, Bogdan, could you please mute yourself?
Okay. So it's a situation when the data scientists are not ready to use data just because data should be prepared somehow for them. And it means that every time the data scientists try to access data, some kind of data engineer should work together just with the data scientists to prepare this data. It's quite complicated approach just because it's just really long. It takes a long time just to prepare data for training models, for extracting features. And that is why Python and SQL is at the moment languages for data engineering. So we are migrating, I would say, from Scala and Java to SQL and Python.
And by the way, maybe off top, but this presentation also previous, it's mentioned when we mention about some streaming process. I think it's a really good practice to use for brainstorming session, event storming approach. It's correct assumption or not? If you're just planning architecture on high-level architecture view, you are using event storming approach.
So I would say it's more related to microservices than classical data architecture. Because it's probably part of the CQRS and event sourcing model. In a data architecture, there are, I would say, 3 main focuses. The first one is data integration, and I would say low latency data access. The second one is data consolidation, and the third one is machine learning and the scalable platform for machine learning. So actually, I had experience in a data delivery team when we prepared data for microservice architecture and extracted data using CDC from the legacy applications, and then actually prepared this data to load to in-memory caches for microservices inside the Pivotal stack. And that's not common approach for data engineers. Data engineers are mostly involved in those 3, I would say, 3 types of projects: integration and low latency, consolidation, data lakes, analytics, etc., and machine learning. So event source is a good approach, but again, it's not a part of data engineering at the moment. More questions?
I don't see any additional question from our chat. So maybe if someone want to ask something, clarify, so please share your question from the chat.